Hello students, this is Skaggs. I'm going to create this video showing how to use SageMathCloud in order to solve some of the problems that you see in our mechanics and materials related curriculum. And so specifically this problem statement could be in the chapter 3 region of the MECET textbook that we're currently using for the 423 class. It's basically talking about analyzing a key used in a power transmission situation and trying to figure out if the proposed key design is acceptable. And so the details of the problem you can see in the problem statement. I'll zoom in a little bit here on the hand calc side of things. You basically have an electric motor. It's spinning at 2,000 RPMs. It's rated at 50 horsepower. It's running a shaft that has a diameter of 1.25 inches. The key that connects the shaft, say, to the gear or V-belt sheave, whatever it may be, has a length of 5/8 of an inch, a side length of 1/8 of an inch, and is a square cross section. It's made from AISI 1020 cold drawn steel, and the questions are, what is the shearing stress experienced by the key, and also what is the resulting factor safety with respect to the yield strength and shear of that 1020 cold drawn material. And so hopefully after you've got through the first portion of mechanics and materials, you'd feel pretty confident in solving these problems. I've got the solution kind of mapped out here if you were doing it by hand. One thing you've got to do is figure out the actual torque that the shaft is experiencing. And so here we've got some relationships which relate the power in horsepower, the torque in inch-pounds, the N was the angular velocity in RPMs. That 63,000 is just a big conversion factor to make sure those units work out correctly. And we solve for the torque. Then, of course, you've got to relate the torque to the actual shearing force that's trying to, say, cut this key right in half along its length there. A little bit of geometry work there, and you can relate the force to the diameter of the shaft. And then after you get the force, you can now look at the key itself. You know the shearing force. You've got to figure out that area and shear, which I've got kind of shaded in red there, to get the shear stress there. That's a direct shear stress application, and you basically would think of the shear stress being uniform all in that shaded area. All that looks like around 32,256 psi. After that, we need to know some material properties. Yield strength of 1020 cold drawn steel is roughly 64 ksi. That's again from our MECET textbook that we're using. And the back in the appendix there, you go from the yield strength, that S and Y is basically from a pure tensile test. You get to the yield strength and shear, and then you can solve for the resulting factor safety. Here, generally, you want to keep these pins from experiencing plastic deformation, so 0.99 is just under the minimum threshold of that. For 1, you would experience it just being on the brink of plastic deformation. Anything less than 1, we'd say plastic deformation has been predicted. And so here you might want to redesign this key so that you can stay away from that realm of plastic deformation. And so that's a very quick run through of kind of the theory behind this. But what if we wanted to actually solve this using Sage? How would that work out? And so that's what we'll do next. I've got a worksheet open here, and so all I've done is created a kind of multi-line comment here in order to write the problem statement out. And so one of the first things I would do is look at declaring all my variables. And so I'll just make a comment here, variable declaration. And so let's start picking things out of the problem statement. One thing we know is that the power that's trying to be transmitted is 50 horsepower. So I'll just call power P and call it 50. And I'm going to make sure I remember that it's in horsepower by putting a comment after the 50 there. That way here I'm declaring that, hey, the power is 50 horsepower, but the units HP, of course, are not read by the Sage software. It's just a comment out piece of text. The next thing I know is it's spinning at 2,000 RPMs. And so just like that, I've got units of RPM. Let's keep that consistent. The diameter of the shaft, so we'll call D underscore shaft, is 1.25 inches. We've got the length of the key, so L underscore key is 0.65 inches. And the side of the key is 0.125 inches. And so that's a very quick way. I'll hit Shift Enter to evaluate all those in order to get this information. Here I don't really like the way that's doing that. I don't really want to see that new line stuff. And so one thing we can do is just something like this. We'll just go through and manually comment all that out. And if I do it this way, I shouldn't need the triple apostrophes. And so give me 1 second to kind of clean this up. There we go. And so now that I've got my variable declared, what's the first thing I want to do? I want to solve for torque. And so I know the relationship here, power is Tn over 63,000. And so notice here in the hand calcs, I have to do the algebra in order to isolate the torque and then plug my values in. Well, instead of doing that, let's let Sage do the algebra for me. Sage is probably better at algebra than I am. And so what we'll do is have Sage work out the algebra and just tell me what the torque is. And so first I'll just make a comment here, torque calculation. And so what do I need? Well, let's define T as a symbolic variable that we can hold stuff with. And let's just say solve. And then in brackets, we'll put our equation that we know. We know power is equal. Here I'm using, notice, the double equal sign. And that was T times N divided by 63,000. And I want to solve that for T. And so you can see the syntax here. I'm using the solve command here. And then I've got an open parentheses, and then I've got an open bracket. Type my equation that I know. Here, P is a known value, N is a known value. All I'm trying to get at is T is the unknown, and I'm solving it for T. And if I hit Shift Enter, notice I've got right here, T is equal to 1,575. The units on that are going to be inch-pound. But I can't really access T at this point, and so one thing I can do is do something along the lines of, if I want solution 1 is equal to this, and so now I'm just storing the solution in a variable. If you want to know the type of the variable, you can just type in type. It's a sequence again. We've seen this before in the solving a system of equations. And so here I could do something like show the solution, just to get that showing again. And if I wanted to set T equal to the actual right hand side, the 1575 part, I would do T is equal to the solution. Here I just have the one square bracket, so 0. And I would say .RHS here to grab the right hand side. And finally I'm going to write a note to myself, print torque. And I'll do string, put T in there, and have it in inch-pounds there. And so notice what I've done here. We've used the solve command in order to solve for T. We're showing the solution here, that is this part here, and then we're picking out the 0th element in that sequence, which is the only element that's there, and we're grabbing the right-hand side, the 1575, and storing it in T. And then we're saying, let's print the text torque, colon, with a space, plus, now we're going to add a string. So str converts the T to a string so it can be printed. And so it's just giving me the value, 1575, and then I'm hitting plus, and let's add some more text, plus space inch-pounds there. And so that gives me a nice readout that I can read torque is 1,575 inch-pounds, which is great. Next thing, we just come down, here's our shear force calculation. Very similar process here. And so we'll just run through that very quickly. Here's our shear force calculation. We'll need a new variable F so we can solve. And so same process as last time. Solve. If I can type, here we are. And so what's the formula? Well, come back to our hand calcs here. It's just this first line here. The torque is equal to F times the diameter of the shaft divided by 2. And so let's just type that in as our known equation. And so we have here T, notice we're going equals now, is the force times the diameter of the shaft, that's d underscore shaft divided by 2. And so this part that I'm highlighting now, that is my known equation that relates the torque, which is our 1575 inch-pounds, to the force that we're trying to solve for and the diameter of the shaft. And so we'll just say, hey, solve this for F for me. It looks like it's 2,520. And again, I'll do the usual thing here, except for here I'm going to go one step farther. Instead of having this intermediate step that'll say solution 1, I'm just going to say F is equal to the solve this 0.RHS to compact it a little bit, and we'll see if we can do this. Let's call this shear force plus string F plus pounds there. And so there we just eliminated one line of code after we got the hang of it and said that, hey, the shear force is 2,520 pounds, which looks good. Next, we refer back to the hand calc, so it was stress calculation for the shear stress calc. And so we should use a comment line to kind of mark my code, what I'm doing in each step. For the shear stress calculation, the formula we know is tau is equal to force over area and shear. Well, it's already solved for tau, so we don't really have to use solve anymore for this one. So I can just say something like tau is equal to the force divided by the area and shear. But what's the area and shear? Well, that's just the length of the key times the side length of the key. So you've got the length in one direction times the side of the cross section here, which is good. And so here we'll just say print shear stress plus string tau plus unit is PSI. And so it looks pretty good, 32,256 PSI, which matches our hand calc, so we're doing good so far. But do we really need all these zeros? Probably not. And so here we can just say, well, let's round this to just 2 decimal places. And I missed one parenthesis there. That's why it is mad. And so let's come right here, put the second parentheses, and there we go, 30,256. Looks better. And so at this point, that was the first part, right? Determine the shear stress and the key. And so we've already got that part nailed down. It's right here. The next is the resulting factor of safety. And so let's do that part now. So factor of safety calculation. And so the factor of safety is in, so I'll just call it var in. And before I get to the factor of safety, I need to know the yield strength and shear of the material. And so let's make a variable hold that. Yield strength underscore shear is equal to what? Well, that's the half the yield strength and tension. We said the yield strength and tension was roughly 64,000, so I'll just say it's that divided by 2. And then how do we solve for that? Usually the formula is that the design shear stress tau d is S sub ys over n. And so that's the one that comes to mind. Our design shear stress we would set equal to the tau value, the shear stress we've already calculated. And so here I'll use solve again to do the algebra for me. And it would be tau is equal to that yield strength and shear value. And we divide that by n. And we're solving for n. And so this should give us an output here. Notice here it says tau is not defined. I can come back here and just hit Shift Enter and run that. F's not defined, so it's going to cascade all the way up. And so in these cases, don't worry. First thing I suggest doing is hit Control A and just running the entire worksheet to see if we can solve this. And it looks like somehow I lost my last line there. And so I'll just retype that quickly. And so tau is equals to the yield strength underscore shear divided by n, and we're solving that for n. There we go. And so you can see n is written as a fraction. Again, I'm going to do the very same thing as I'm doing up in line 23 there, just so I can get the actual value out so I can print it. And so n is equal to the first element in the sequence. It's going to be an expression. Now with the right hand side. And so that is good. And then I'll just say print factor of safety, mapping it to a string. Here I'm going to go ahead and round the string to 2 decimal places. And there's no unit. And so just like that, we have the factor of safety at 0.99, which is exactly the same as the hand calc I have below here. And so you can see this process of using Sage mirrors the hand calculation just right after another. Some of the solve commands are somewhat tedious almost. some of the things we're doing, like this item down here, it would just be pretty easy to say n is equal to the yield strength and shear divided by tau. But as you get to more complex problems, it'll be easier for you to use the solve command to solve some nasty equation for a given unknown than having to work through all the algebra and then just type it into your calculator or type it into Sage here. That way you just get in the habit of using that solve command, and as you get to more complex problems, you might have a little bit more typing, but the process is all going to be the same. And so hopefully this helps you get a feel for how Sage can be used to solve problems in the 424 course or 423, or basically any other course that you have involving these style of calculations. And so, as always, thank you for watching the video, and hopefully this helps get you started with using Sage.